Hello, my name is Gevork Gevorkyan. I'm in my 5th year of the physics Ph.D. program at ASU, and I work in Dr. Sidarth Karkare's photoemission and bright beams lab. My work is primarily about photoemission sources and electron acceleration, and I've spent the past several years designing and commissioning a 200 kilovolt cryogenically cooled DC electron gun and cathode diagnostics beamline. The scientific community is pushing toward higher brightness electron beams, particularly because it is critical in the ultrafast applications such as X-ray free electron lasers, ultrafast electron diffraction, and ultrafast electron microscopy tools, and even particle colliders. These tools are responsible for a large portion of modern-day STEM research, and they directly benefit from having brighter electron beams from the source because it makes them operate better with higher energies, with higher resolution at larger spatial scales, providing results at shorter time scales, and so on and so forth. Brighter electron beams would even reduce the cost and the size of these tools themselves, which cost millions to tens of billions of dollars and can take up anywhere from a small lab size for microscopes to entire city sizes for colliders. Improving the beam brightness for these tools would have long-reaching effects across STEM overall. My project homes in to the initial part of these electron accelerators, the photoinjector, and I'm trying to answer the question, can we juice up electron accelerators from the source? I think we can, and I think the juice is worth the squeeze. Here's the story. A useful definition for beam brightness is the beam current divided by the transverse impedances. Impedances is the area the beam occupies in phase space where the horizontal axis is position and the vertical axis is momentum. The root mean square position spread, RMS momentum spread, and correlation term all come into play here in the definition of impedances. For high brightness, we want to maximize our current and minimize the impedances. By looking at what affects the charge output and the transverse impedances, we landed a useful relationship where the brightness is somehow proportional to the electric field used for accelerating the electrons and inversely proportional to the mean transverse energy, MTE. This term MTE is essentially the RMS transverse momentum spread of the beam as seen in the impedances relationship. We also like to think of it as the temperature of the beam. For higher brightness, we want to maximize the electric field and minimize this MTE. Now, let's look at a model for how photoemission works. In the drawing here, we have energies going on the vertical axis and position on the horizontal, where the upward step is the energy required for the electron to leave the surface and exit to vacuum, also known as the work function. On the bottom left, there are electrons distributed at the Fermi level with varying energies. We first excite them up with an incoming photon that has energy h nu. Then the portion of the Fermi distribution that overcomes the work function is emitted with some excess energy. Dowell's model of photoemission says that the MTE of the emitted beam is about 1/3 the excess energy. And for context, this is in the range of hundreds of millielectron volts for modern accelerators, typically in the range of 300 MeV or so. If we happen to tune the light so we were to have excess energy of 0 or even slightly negative, then only the tail of the Fermi distribution is emitted. In this situation, the MTE goes to the thermal limit, kT, which is the photocathode lattice temperature times the Boltzmann constant. For reference, room temperature translates to 26 millielectron volt MTE, and if we were to cryogenically cool the cathode, then the MTE could go to the low single digits in millielectron volts, a factor of 100 improvement over photocathodes used today, although we would emit significantly less electrons at threshold. With that said, temperature is not the only factor for MTE because we're really talking about the RMS transverse momentum spread. The other factors convolute and especially pop up when we're trying to reach the low single-digit millielectron volt MTEs. Things like nonlinear photoemission, laser-induced heating, disorder-induced heating, photon-phonon scattering effects, and nanoscale roughness effects, to name a few. Some of my early work in the field particularly focused on the effect of nanoscale surface height and work function variation. This work helped me to motivate the need to build our electron gun, so let me tell you what we did and what we learned from it. Let's look at two cartoons demonstrating surface height variation and work function variation separately. In the first image, the equipotential lines bend along with the surface height variations, and the electrons are accelerated by these bent electric field lines, which means we want smaller electric fields to reduce this effect. Uh-oh, we needed higher electric fields to increase the beam brightness though, so this is a big challenge for us. Well, in the second image, the similar but reciprocal effect happens with the work function variation. Electrons that stay close to the surface for longer are pushed by the work function variation, which means we want larger electric fields to go away from the surface faster to reduce this effect. In reality, both surface height variation and work function variation happen together, and the result is not straightforward to predict. Here, I show an example of a photocathode measured on the atomic force microscope and Kelvin probe force microscope in our lab. The axes show the spatial scale, XYZ in nanometers, and the color map shows the work function variation in volts. I wrote a particle tracking code to compute the contribution of roughness on MTE from real photocathode surfaces like the one you see here. To track electrons, we need to know the electric field very precisely between the cathode and anode. I used a spectral method to solve Poisson's equation given 3 boundary conditions. 1, the cathode surface has the measured work function. 2, the anode is grounded some distance away from the cathode. And 3, the surface is repeating, which is a safe assumption because photocathodes are crystalline surfaces. The electric potential is solved using products of sines and cosines in the transverse dimensions labeled x and y, all with an exponential decaying term in the direction toward the anode labeled z. These functions are a spanning basis, and the electric field is solved using the first condition, knowing the potential everywhere between the cathode and anode. This tells us the acceleration the electrons would experience at any point after leaving the cathode and lets us track how they evolve as they reach the anode. So what did we learn from this code? The code outputs this plot where the black solid line is the estimate of the combined roughness effect on MTE versus the strength of the electric field. This work showed us that the roughness of polycrystalline photocathodes could contribute to the MTE as much as the temperature effect. This happens both at low fields and high fields, and the only way to get away from this is to not have roughness by using epitaxially grown or single crystalline ordered surface photocathodes. For a more thorough explanation of this particle tracking code and the results, please refer to our publications on this work under my name on Google Scholar. So what's the best way to lower the MTE, lower the emittance, and therefore increase our electron beam brightness? We want a tunable wavelength laser so we can emit from the threshold energy. We want to cryocool our photocathode to reduce the lattice temperature. We want a high quantum efficiency photocathode because we want to emit more electrons at the lower temperature, and also because nonlinear photoemission effects will be mitigated by having to use less photons. And we want the photocathode to be single crystalline or epitaxially grown so we don't hit a roadblock with the surface roughness. So where do we find these special photocathodes exactly? Well, in the surface sciences world, they already exist, and they have been tested at low voltage. The single crystal ordered surface of copper 100 produced a world record low MTE of 5 millielectron volts at cryogenic temperatures at threshold, albeit with low quantum efficiency. And recently, researchers demonstrated epitaxial growth of cesium-3 antimonide, which is a material that really fits the bill when it comes to low MTE and high quantum efficiency photocathodes. So these photocathodes exist. They have been tested at low accelerating voltages, and we can buy them or we can grow them. But in the accelerator world, we don't typically use these special photocathodes because no electron accelerator can use them to their full potential due to the way accelerators are designed today. All of this is why I designed and built the 200 kilovolt cryogenically cooled DC electron gun here at Arizona State University. Let me show you it now. Here is the ASU 200 kilovolt cryogenically cooled DC electron gun. This electron gun utilizes a custom-made photocathode holder, which is compatible with the mounting system of commercially available surface sciences tools, making the use of single crystalline or epitaxially grown photocathodes possible in this electron gun. The electron gun has a cryostat where a liquid helium refrigeration system can continuously flow liquid helium to cool the cathode. And my electrostatic design includes a cryogenic shield as well to mitigate the black body heating of the chamber body to the cathode surface. This lets us reach temperatures down to 35 Kelvin at the photocathode surface, which translates to a 3 millielectron volt contribution to MTE from temperature, plenty low enough to produce the best results to date. The gun has been conditioned to high voltage and has reached beyond 200 kilovolts. The gun sits on the left here in this 3D model of our photoemission and bright beams lab. The lab is equipped with a tunable wavelength OPA laser, allowing for photoemission at threshold energies for various materials. And this lab is particularly unique because there is a photocathode growth chamber connected to the same vacuum line as the electron gun, along with multiple surface preparation and surface characterization tools. This means that the photocathodes never leave the vacuum system, can be measured before use in the electron gun, and can be measured after use of the electron gun as well. All of this will add credibility to our upcoming results. The electron gun fires directly into a diagnostics beamline, which will be used to demonstrate the photocathode performance. All of this and more makes my electron gun a fantastic test bed accelerator for special photocathodes. You can find out more from our publications and conference proceedings listed under my name on Google Scholar. At present, the diagnostics beamline is set up to look at tiny portions of the electron beam at a time using a pinhole scanning technique. A pinhole aperture crops the beam, and a drift space lets us to directly measure the momentum spread of the beam on a thin scintillating YAG screen, which reacts to electrons that land on its surface. This tells us not just the MTE, or the transverse RMS emittance, but rather the full 4D phase space of the electron beam in its entirety. We're working on measuring an electron beam from a cesium-3 antimonide photocathode grown in-house, and I'm looking forward to publishing results on that work later this year. This is just the first step of many uses planned for this system. All of this will be used to answer the question, can we juice up electron accelerators from the source? Using this beamline, we hope to produce brighter electron beams than ever seen before and motivate the next generation of photoemission-based accelerators. I sincerely appreciate my advisor, my lab mates, all the wonderful staff at ASU, and all my collaborators who have helped me along the way. Thank you especially to the NSF Center for Bright Beams for providing me with funding for this work. The things that I've discussed were just a small bit of what we've been doing in our lab. Keep an eye out for my upcoming publications and proceedings, which you will find under my name on Google Scholar. I hope you've enjoyed learning about my research work, and if you have enjoyed this video, please leave me a like and leave a comment down below. It would mean a lot. Make sure to subscribe for more research content from the ASU Physics YouTube channel, and thank you for watching.